Okay, so today we're going to find a particular solution to the ordinary differential equation 4d2x by dt squared equals 3dx dt minus 6x. We're familiar, aren't we, now with roughly what this is relating to? Probably some sort of mass oscillating, some sort of damping effect is the second term that is to do with the velocity, and some sort of spring or restoring force. Okay, and we got some boundary conditions. When t equals 0, at the start, in other words, it's displaced 3 meters or 3 units away, and it's got an initial velocity of 4. Right, what's step 1 on that piece of paper that we had? Yep, so form the auxiliary equation, in other words, by changing these differentials to m's. So first of all, we're going to look at this solving the auxiliary, noting that the right-hand side 0, which means it's a free oscillation. There's no driving force. It's just been given an initial impulse, and it's going to die away naturally to 0. It's a homogeneous differential equation. So what is the auxiliary equation going to be then, Liam? Brilliant. And now we can solve that quadratic equation. Somebody like to remind Nigel and Matt what the formula is for the... Thank you, Mark. So if you want to... A equals, B equals, and C equals. A equals, B equals, and C equals -6. Good. So plug those numbers into the quadratic formula and find out the values for m for me. So putting those values into the quadratic formula, we get m equals plus 0.9 or minus 1.65. So therefore, we have two real, distinct, or different solutions. So the general solution has the form so we've got the general form y equals ae to the k1x plus be to the k2x, and then we can put our values in for n that we just found. So that's the first step, step 1, okay? Form the auxiliary equation and find the general solution. In fact, that's even up to step 2 now, isn't it? Put those values into the general solution. Now all we've got to do is find our values for a and b. So typing this into autograph, y equals a e to the 0.9x plus b e to the minus 1.67x, here is the function. This is our start point, remember. We're not interested in anything that happens to the left-hand side of 0. So we can drag the whole thing across, actually, if I just pull this over here. We're only interested in this bit, really. Now we can change the values of a and b. Remember, we're going to calculate a and b in a second, but let's just see what happens. If I change a and b, which by default are set as 1, then if I increase a, I increase b, we change the start point for start off, and also the way that the curve behaves, okay? And so we're going to find these values for a and b now, which is going to give us an idea. of where this thing starts off and how it's going to behave after that point. So although we've got a general solution at the moment, we've got a general idea what this thing is going to look like, we want a particular solution for this problem. So we need to find A and B. So with these initial boundary conditions, at t equals 0, x equals 3, and dx by dt equals 4, let's form these two simultaneous equations. So from our initial general solution here, we now put in our boundary conditions. When t equals 0, x equals 3. So putting in the boundary condition, x equals 3, when t equals 0, we can form our first equation. So y, which is our displacement vertically from x being generally time, so y equals 3 a e to the 0.9 times 0 x equals, sorry, y equals 3 t equals 0, shouldn't have been here. Yeah, right. Just pause here. I've mixed myself up a little bit with my notation here. This, of course, is time, and this is our displacement from 0. So in this sense, x equals 0 represents our y. So this should be, this is where I went a little bit weird, that should be really x, our displacement, and this should be time. That's the trouble with fiddling around with your variables. It's y and x generally, but of course we're now relating it to an x and a t, aren't we? So that would have been better. So when t equals 0, x equals 3. So the first one we've got is 3 equals a e to the 0 plus b e to the 0. So what can we say from that? Anything to the power 0 is anything to the power 0 is 1. So 3 equals a plus b. So that's our first equation. Now, our secondary bound, that's easy. Our secondary boundary condition is a little bit more complex. And when we get to more complicated functions where we've got combinations of exponential and sine functions, that's not quite so straightforward, as we'll see. However, what's our second condition? Dx by dt equals 4, was it? When t equals 0. Yeah, 4. So what have we got to do with this now? We've got this thing, remember, x equals a e to the 0.9t plus b e to the minus 1.65t. What are we going to do with that now? Yeah, that's, as I was saying a minute ago, that's because I've mixed up my variables. Instead of y and x, we're using x and t. So sorry about that. I'm told that dx by dt equals 4 when t equals 0. So what have I got to do with this function? Differentiate it to get dx by dt. Do you remember how to differentiate an exponential function? Yeah, the 0.9 comes down, well done, and goes in front. And what happens to the power? Stays the same. So that will now become minus 1.67 b e to the minus 1.65. Why am I putting 7 there? I don't know. T. No, that's for a general function. For an exponential function, it stays the same. For this particular exponential function where the base e, that's this very, very unusual function where the differential is the same as the original function. Now t equals 0, so we can write 4, because that's the value for the differential. Remember what this differential is, it's the speed. So what we're saying is it's got an initial speed at time equals 0 of 4. So there's a gradient on this curve. Equals 0.9 a e to the 0 minus 1.6 b e to the 0. And anything to the power 0, Nigel, is 1. So therefore, 4 equals 0.9a minus 1.65b. And that's equation 2. So solving these simultaneous equations, you've got two equations. One, a plus b equals 3. 2, 0.9a minus 1.65b equals 4. How do we solve those simultaneously? So from 1, a equals b minus 3. This is a substitution method. We rearrange the first one, that's generally the one that's going to be quite straightforward, to read a equals b minus 3. So we can now do what? Substitute into, right, good. So what would we write? Okay, good. 0.9 into b minus 3, because that's substituted for a, minus 1.65b equals 4. Now solve that for b, please. I'll just pause while you do that. Yeah, it is. Backtracking, note the deliberate mistake. Who told me it was b minus 3? It wasn't you, was it, Mark? Nope. A equals 3 minus b. So that's going to change this, isn't it? Thank you for that, Mike. That's going to be a 3 minus b, which is going to change the whole thing. Yeah. So, sorry, this is wrong. Start again. So b equals negative 0.51 now, sorry, okay? Now we've got b, of course. All we've got to do is substitute that back into equation number 1 to find a. So finally, a equals, let's get it the right way around this time, 3 minus b. 3 minus 0.51, so it's 3 plus 0.51, 3.51. So a equals that and b equals that. And if you were doing this, of course, for real, and you didn't have me standing here getting it all wrong, how would you check? Put your values for a and b back into equation 2 and see if you get 4. Okay? So would you like to do that just to finally make sure you're not making mistakes? So check in 2. Always a good idea. If you're doing an assignment question for me on this and you're doing this, I would recommend you do that. If we look at the function, let's look at what's happening here and try and relate this to reality if we can. Because, of course, what we've done is you just put an example. Remember that original problem we had this solution, here. And it was a solution to a differential equation that had a mass, initial mass, some restoring force, K, and then this damping effect. It looks to me, if you look at this function, that, remember what we've got here, time against x, so the displacement x is actually increasing. And so what's happening here is the restoring force is possibly not enough to bring it back, so therefore it's continuing to move away. It's not coming back. There's not going to be any oscillation. If we look at this and we were to zoom in on this part, we'd find that it's starting at 3, which agrees with our initial condition. And if you went to autograph and zoomed in at that point, you'd see that. And also, the gradient of the curve at this point would be R4, our original dx by dt. So it gives you your initial conditions and then tells you what happens to this object, whatever it is, as time goes by. So it's actually just moving further and further away from our start point. Okay, what I want you to do now is to look at this question. Okay, there are a few of these questions, so have a go at this one on your own now. Follow exactly the same steps as we just did for this particular problem. You've got a second order differential equation here, and you're given some initial conditions. When x equals 0, y equals 4, and dy by dx equals 9. So exactly the same idea. When you've done it, plot it on an autograph and see what it looks like.